All right, let's get into it. So you've just built a brand new AI model. It's sleek, it's powerful, it feels like the future. But here's the real question. Is it actually any good? Today, we're going to slice right through the hype and figure out how you really know if an AI is performing well.
I mean, really think about that. You've poured all this time and energy into your project. It's up and running, it's giving you answers. But when the stakes are high, can you actually trust those answers? How do you know for sure that it's going to make the right call when it really truly matters?
To make this less abstract, let's use an example. Imagine we've built an AI to scan thousands of photos, looking for one specific, really dangerous invasive insect. If our model misses just one of them, it could spark a massive infestation, cause millions in damage, and just wreck an entire ecosystem. The stakes, they're about as high as they get. So, how do we measure this thing? Well, the first place pretty much everyone goes, the most obvious intuitive answer, is to just look at its accuracy. Accuracy is super straightforward. It's just asking, out of all the guesses the model made, what percentage did it get right? Simple. If we show it 100 photos and it gets 99 of them correct, that's 99% accuracy. Sounds fantastic, doesn't it? I mean, look at that. 99%. You'd get an A+ for that in any class. It seems like we should be popping the champagne, right? Let's deploy this thing. It's practically perfect. Or is it? And this is where it all gets so fascinating. What if I told you that in our high-stakes insect problem, a model with 99% accuracy could be, well, completely and utterly worthless? To really get why, we need to look past that single flashy number. We have to dig a little deeper into the kind of data our model is actually dealing with. And here's the hidden trap. It's called an imbalanced dataset. Think about it. Our dangerous insect is, hopefully, pretty rare, right? Maybe only one photo out of 100 actually has it. Well, a lazy AI could just learn to say no insect every single time. It'd be wrong on that one photo, sure, but it'd be right on the other 99. Its accuracy, a beautiful 99%. Its actual value, zero, zilch. It would fail at the one job we hired it to do. So, this is the key. We have to understand the types of mistakes our model makes. And for that, we use this amazing tool, the confusion matrix. It breaks everything down. A true positive, that's when we correctly spot an insect. A false positive is a false alarm, but the false negative, that's when an insect slips right past us, totally undetected. That's the catastrophe we're trying to avoid. Now, this matrix lets us ask much, much smarter questions. We can move beyond how accurate is it and start talking about two incredibly important metrics that are often in a tug of war: precision and recall. And I love how this slide just boils it down to two simple questions. Precision asks, when the AI yells insect, how often is it actually right? It's all about reliability. Recall, on the other hand, asks, of all the actual insects that are out there, what percentage did our AI manage to find? That's all about completeness. Let's drill down on precision for a second. It's the number of correct positive guesses divided by all the positive guesses the model made. So the goal here is to cut down on those annoying false alarms. High precision means when the AI raises its hand, you can bet it's right. And recall, well, recall is all about not letting anything slip through the cracks. It's the number of correct positive guesses divided by everything that was actually there to be found. This is all about crushing those false negatives. A high recall model is thorough. It doesn't miss much. But here's the catch, and this is so important. In the real world, you can't just have it all. As you tweak your model to get better at one of these, it usually gets worse at the other. And that leads us to this: the great trade-off between precision and recall. So how do we manage this balancing act? Well, we have a dial we can turn, called the classification threshold. Just think of it like a sensitivity setting. It basically tells the AI how confident it needs to be before it's willing to shout, "Hey, I found an insect." Let's see how this plays out. If we set a really high threshold, we're telling our AI to be super cautious. It'll only flag an insect if it's absolutely sure. The result? High precision, almost no false alarms. But it's probably going to miss a few real ones, so our recall will be low. Now, what if we lower the threshold way down? The AI gets trigger happy. It'll flag anything that even kind of looks like our insect. We'll catch them all, high recall, but we're also going to get a ton of false alarms, which means low precision. See the trade-off? Okay, so we've got this dial we can turn. But what if we could see the entire picture all at once? What if we could see how our model performs at every possible setting of that dial? Let's take a look at the model's final report card.
And this is that report card, the ROC curve. It's just a graph that shows you the whole trade-off. On the vertical axis, you have your recall, how many real insects we catch. On the horizontal axis, you have the false positive rate, how many false alarms. What you want is a curve that pushes as far up and to the left as possible. That means you're catching a lot of the right stuff without flagging too much of the wrong stuff.
Now, comparing a bunch of different curves can get a little messy, so we simplify it all down to one single number, the AUC, or area under the curve. It's a score from 0 to 1 that tells you how good that whole curve is. A 1.0 is a perfect model. A 0.5, you might as well just be flipping a coin. This is kind of the ultimate single number grade for your model's potential.
Whew, okay. We have covered a lot of ground here, from that deceptively simple accuracy all the way to precision, recall, and AUC. So now let's bring it all home. How do we pick the right metric for our job?
This slide is basically your cheat sheet. It's all about the cost of being wrong. If missing something is the absolute worst-case scenario, like our invasive insect or a medical diagnosis, then you optimize for recall. Period. If false alarms are the bigger headache, like marking an important work email as spam, you optimize for precision. And good old accuracy, as you can see, you really want to avoid it with imbalanced data.
Which brings us right back to where we started. For our invasive species detector, what's the real cost of each type of mistake? What's worse, a false alarm where some expert has to look at a photo of a harmless bug for 30 seconds, or a silent invasion where we miss the one insect that starts a plague? I mean, it's not even a question, right? It's crystal clear. A false negative, missing that one insect, is infinitely more expensive than a false positive. The consequences are just devastating. So for this problem, we have to forget about that seductive 99% accuracy and tune our model for one thing and one thing only, maximizing recall. We've got to catch every last one, even if it means we have to deal with a few more false alarms along the way. So the next time you hear someone brag about an AI with 99% accuracy, you'll know to ask the smart question, what's the 1% they're not telling me about? Because choosing the right metric isn't just some techie decision. It's about deeply understanding what failure really costs in the real world. If you want to dive deeper into this kind of thinking, definitely check out the AI Product Management Playbook on LinkedIn. Thanks so much for tuning in to this explainer.